In the previous lecture, we discussed relationship between osmotic pressure and vapor pressure, van 't Hoff's theory of dilute solutions, some examples related to van 't Hoff's theory and concept of activity and activity coefficient. In the continuation, today we are going to discuss abnormal colligative properties by association and dissociation, abnormal molecular masses again by association and dissociation, van 't Hoff factor and calculation of van 't Hoff factor. Actually, the colligative properties depend upon the number of solute particles present in the solution. All the relationships derived for the colligative properties hold good only when there is no change in the molecular state of the solute. But if the number of particles of the solute in solution changes, colligative properties also change. Number of particles of the solute can change by two methods, one by association and by dissociation. If the solute is an electrolyte, it can dissociate into number of particles. As a result, total number of particles of solute increases in the solution and all the colligative properties also increase. In case of association, two or more particles associated to give one giant particle. Hence, the number of particles of solute decreases in the solution and all the colligative properties also decrease. Thus, the normal value of colligative property is proportional to the number of particles solutes originally taken, and abnormal value of colligative property is proportional to number of particles of solute after association or dissociation. Hence, the ratio abnormal colligative property upon normal colligative property may have the value either greater than 1 or less than 1. In 1880, van 't Hoff introduced a factor I known as van 't Hoff factor to account for the extent of association and dissociation. Van 't Hoff factor I is equal to abnormal colligative property upon normal colligative property, which is again equal to normal molecular mass upon abnormal molecular mass. Now, relative lowering in vapor pressure will be equal to van 't Hoff factor into mole fraction of solute. Elevation in boiling point will be equal to van 't Hoff factor into molar elevation constant into molality of the solute. Depression in freezing point will be equal to van 't Hoff factor into molar depression constant into molality of solute, and osmotic pressure of the solution will be equal to ICRT, where I is the van 't Hoff factor, C is concentration of the solution, I is gas constant, or we can say it is solution constant in case of solution, and T is the temperature in Kelvin. Now, first we are taking dissociation. Suppose we are taking one molecule of AN, which on dissociation gives N molecules of A. Hence, number of ions produced will be equal to N into alpha, where alpha is the degree of dissociation of the solute. The number of unionized molecules will be equal to 1 minus alpha. Therefore, total number of molecules after dissociation will be equal to 1 minus alpha plus N alpha. Hence, van 't Hoff factor I will be equal to number of particles after dissociation upon number of particles before dissociation. As we have taken one particle before dissociation, hence I will be equal to 1 minus alpha plus N alpha upon 1. That is, alpha will be equal to I minus 1 upon N minus 1. Let us take an example to understand this dissociation in a better way. The osmotic pressure of a 0.01 molar solution of calcium chloride and sucrose at 298.15 Kelvin are 0.605 atmospheres and 0.224 atmospheres respectively. Calculate the van 't Hoff factor and degree of dissociation of calcium chloride. We know that pi observed upon pi normal will be equal to 0.605 upon 0.2005 according to the problem, and pi observed upon pi normal will be equal to I, which we are getting 2.70. As calcium chloride is an electrolyte, dissociation will take place as calcium chloride will break up in 1 ion of calcium 2 plus and 2 ions of Cl minus. Therefore, I will be equal to 1 minus alpha plus 2 alpha, which is equal to 1 plus 2 alpha. Hence, 1 plus 2 alpha is equal to I. Here alpha is degree of dissociation of calcium chloride. By equating, we can get alpha is equal to 0.85 or 85% dissociation. There is another example to understand dissociation. Find the osmotic pressure of an aqueous solution of barium chloride at 288 Kelvin containing 0.39 grams per 60 ml. The salt is 60% dissociated. Molecular mass of barium is given as 137 and that of chlorine as 35.5. As 60% dissociation is given, hence alpha, that is degree of dissociation, will be equal to 60 upon 100 means 0.6. For an electrolyte solution, pi V will be equal to I into N R T, where I is want of factor. Volume is 60 ml, hence it will be equal to 60 upon 1000 liters. Number of moles will be equal to weight upon molecular mass of barium chloride, that is 0.39 upon 208, and temperature is given as 288 kelvins. Now we have to calculate I first. I will be equal to 1 minus alpha plus 2 alpha because barium chloride dissociates in 1 ion of barium 2 plus and 2 ions of Cl minus. Therefore, 1 minus alpha plus 2 alpha upon 1 will be equal to I, or we can say I will be equal to 1 plus 2 alpha, as the value of alpha is 0.6. So, putting this value of alpha, we can get I equal to 2.2. Substituting this value of I in equation 1, we will get pi equal to 2.2 into 0.39 upon 208 multiplied by R, which is equal to 0.0821 liter atmosphere per mole per Kelvin, multiplied by temperature 288 Kelvin, and divided by volume, which is equal to 60 upon 1000. This is equal to 1.6256 atmospheres. Let us take another example to understand want of factor in case of depression in freezing point. A certain mass of a substance when dissolved in 100 grams of benzene lowers the freezing point by 1.28 degrees Celsius. The same mass of the solute dissolved in 100 grams of water lowers the freezing point by 1.4 degrees Celsius. If the substance has normal molecular weight in benzene and is completely dissociated in water, into how many ions does it dissociate in water? Kf, that is molar depression constant for water and benzene, are 1.86 and 5.12 Kelvin per mole Kg respectively. Now, as we know that delta Tf is equal to 1000 into Kf into Wa upon Wb into Ma. In benzene, the molecular mass will be normal, that is delta Tf is 1.28. Putting all the values of delta Tf, Ma, Mb and Wa in the equation, for benzene we will get 1.28 equal to 1000 into 5.12 into Wa upon normal molecular mass multiplied by 100. This is equation number 1. But in water it is completely dissociated, hence 1.40 will be equal to 1000 into 1.86 into Wa upon experimental molecular mass multiplied by 100. This is equation number 2. As solute behaves normally in benzene and it dissociates completely in water, hence in case of benzene normal molecular mass has been taken, and in case of water experimental or observed molecular mass has been taken. Equating these equations 1 and 2, we will get normal molecular mass upon experimental molecular mass equal to 3.01, that is I equal to 3.01, which can approximately be taken as equal to 3. As the solute is 100% ionized and alpha is equal to 1, Therefore, if we take the electrolyte as AXBY, it will dissociate as XA plus Y B minus, means X ions of A plus and Y ions of B minus. Therefore, we will get total number of ions after dissociation 1 minus alpha plus X alpha plus Y alpha. Therefore, I will be equal to 1 minus alpha plus X alpha plus Y alpha, and as I is equal to 3 and alpha equal to 1, putting all these values, we will get X plus Y equal to 3. Therefore, number of ions given in water will be equal to 3. Now we will discuss calculation of want-of factor in case of association. Let us take n molecules of A which associates to give one molecule of AN. Therefore, number of unassociated molecules after association will be equal to 1 minus alpha, and number of associated molecules will be equal to alpha by n, where alpha is the degree of association. Therefore, I will be equal to 1 minus alpha plus alpha by n, which will be less than 1. Rearranging this equation, we will get alpha equal to 1 minus I upon 1 minus 1 upon n. For better understanding of association, we are taking an example. Acetic acid associates in benzene to form double molecules. 1.65 grams of acetic acid when dissolved in 100 grams of benzene raised the boiling point by 0.36 degrees Celsius. Calculate the want-of factor and the degree of association of acetic acid in benzene. Molar elevation constant of benzene is 2.57 Kelvin kg per mole. As normal molecular mass of acetic acid is 60, therefore, Wa is equal to 1.65, Wb is equal to 100 grams, delta Tb is equal to 0.36 and Kb is equal to 2.57 Kelvin kg per mole. We have to calculate Ma. Now, Ma will be equal to 1000 into Kb Wa upon Wb into delta Tb. Putting all these values, we get Ma equal to 117.79, means it is experimental molecular mass of acetic acid. Now, want-of factor is equal to normal molecular mass upon experimental molecular mass. Normal molecular mass of acetic acid is 60 and experimental molecular mass we have calculated 117.79. Putting both these values, we will get I equal to 0.509. As the acetic acid forms dimer on association, that is, it forms dimer, we have 2 moles of acetic acid giving 1 mole of dimer of acetic acid. Therefore, observed molecular mass upon normal molecular mass will be equal to number of particles before association upon number of particles after association. Putting all these values, we will get degree of association equal to 98.14%, or we can say we get alpha equal to 0.9814. Now we will take another example for the calculation of want-of factor in case of freezing point depression. Phenol, that is C6H5OH, associates in water to dimer. When 0.75 grams of phenol is dissolved in 45 grams of water, the freezing point depressed by 0.255 degrees Celsius. Calculate the degree of association of phenol. Kf, that is molar depression constant for water, is 1.86 Kelvin kg per mole. As normal molecular mass of phenol is 94, the observed or apparent molecular mass M1 can be calculated, for which W1 is equal to 0.75, W2 is equal to 45, delta Tf is equal to 0.255 and M1 we have to calculate. Now, M1 will be equal to 1000 Kf W1 upon W2 into delta Tf. Putting all the values, we will get M1 equal to 121.56. Phenol associates to give a dimer as follows. One molecule of phenol will give half the molecules of the dimers. Hence, observed molecular mass upon normal molecular mass will be equal to number of particles before association upon number of particles after association, or 121.56 upon 94 equal to 1 upon 1 minus alpha plus alpha by 2. Putting all these values, we will get alpha equal to 0.4536, that is, degree of association will be equal to 0.4536 or 45.36%. In continuation, we are taking another example. A solution containing 0.2965 grams of benzoic acid in 20.27 grams benzene freezes at temperature 0.317 degrees below the freezing point of the solvent. The freezing point of benzene is 5.5 degrees Celsius and its latent heat of fusion is 30.1 calories per gram. Calculate the degree of association of benzoic acid if it forms double the molecules, that is dimer. Now we have Kf is equal to RT square upon 1000 into Lf. Here T is normal freezing point of the solvent and Lf is latent heat of fusion of the solvent. Putting all the values, we will get Kf for benzene. Normal molecular weight of benzoic acid is 122. We have W1 equal to 0.2965, W2 equal to 20.27, delta Tf equal to 0.317 and M1 we have to calculate. Putting the values in the equation, M1 equal to 1000 K W1 upon W2 into delta Tf, we will get the value of M1. As benzoic acid form dimer in benzene, hence observed molecular weight upon normal molecular weight equal to number of particles before association upon number of particles after association. Therefore, 1 minus alpha by 2 equal to 122 upon 237.63, and on calculating we will get alpha equal to 0.9732, which we can say that degree of association of benzoic acid in benzene is 97.32%. Now we will discuss how to calculate the osmotic pressure if the mixture of two solutions is given. There are two cases. Number one case is when the two solutions are of the same solute, and case 2 when the two solutions are of different solutes. First we are taking case 1 where the two solutions are of the same solute. Here we can say pi 1 V1 plus pi 2 V2 will be equal to pi of resultant solution into volume of resultant solution, which is equal to V1 plus V2. Here pi 1 V1 are the osmotic pressure and volume of first solution and pi 2 V2 are the osmotic pressure and volume of second solution. There is case 2 where the two solutions are of different solutes. Here we have to consider I, that is want of factor of both the solutions. Let N1 and N2 are the number of moles of two different solutes present in V1 and V2 volumes respectively. Osmotic pressure of the mixture of two solutions will be equal to pi 1 plus pi 2, where pi 1 is the osmotic pressure of first solution and pi 2 is the osmotic pressure of second solution. Now resultant pi, that is resultant osmotic pressure, will be equal to I1 N1 RT upon total volume, that is V1 plus V2, plus I2 N2 RT upon total volume, that is V1 plus V2, or we can say resultant osmotic pressure will be equal to N1 I1 plus N2 I2 into RT upon total volume, that is V1 plus V2. Here I1 and I2 are the want of factors for the two solutes first and second. There is an example to understand the calculation of osmotic pressure of the mixture of two solutions. X grams of a non-electrolyte compound whose molecular mass is 200 are dissolved in 1 liter of 0.05 molar sodium chloride aqueous solution. The osmotic pressure of this solution is found to be 4.92 atmospheres at 27 degrees Celsius. Calculate the value of X. Assume complete dissociation of sodium chloride and ideal behavior of this solution. The value of R is given to be 0.082 liter atmosphere per mole per Kelvin. As osmotic pressure is given to be equal to 4.92 atmosphere, temperature is 27 degrees Celsius, that is 300 Kelvin, and volume of the solution is 1 liter. N1 is equal to moles of non-electrolyte. As X grams of the known electrolyte has been dissolved, hence number of moles of non-electrolyte will be equal to X upon 200, because 200 is the molecular mass of the non-electrolyte. N2 is the number of moles of sodium chloride, which is given to be equal to 0.05. Using the equation pi V is equal to NST for the solution containing non-electrolyte and sodium chloride, we will get pi V equal to N1ST plus N2 into 1 plus alpha ST. Here N2 1 plus alpha ST is used for the sodium chloride solution. Therefore, pi V equal to N1 plus N2 into 1 plus alpha ST. Putting all the values, we will get X equal to 20 grams, as the value of alpha equal to 1, because sodium chloride is 100% ionized in the solution. If the osmotic pressures of two different electrolytic solutions are given, we can calculate the ratio of their degree of dissociations. Let us have an example. 0.01 molar aqueous solution of weak acid HA and HB shows osmotic pressures equal to 0.30 atmosphere and 0.35 atmospheres respectively at 25 degrees Celsius. Calculate the ratio of their degree of dissociation. Now, osmotic pressure of first solution, that is pi 1, equal to C1 S1 T1 into 1 plus alpha 1, and osmotic pressure for the second solution, that is for HB, is equal to pi 2 equal to C2 S2 T2 into 1 plus alpha 2. Equating both the equations, we will get 1 plus alpha 1 equal to 0.30 upon 0.01 into 0.0821 multiplied by 300, or we get alpha 1 equal to 0.218. Similarly, 1 plus alpha 2 will be equal to 0.35 upon 0.01 into 0.0821 multiplied by 300, or we get alpha 2 equal to 0.421. Hence, the ratio alpha 1 upon alpha 2 will be equal to 0.218 upon 0.421, which is equal to 0.52. There is another example for better understanding of van 't Hoff factor for depression of freezing point. A solution of X grams of urea in 500 grams of water is cooled to minus 0.5 degrees Celsius. 128 grams of ice separated from the solution. Calculate X, given that Kf, that is molar depression constant for water, is equal to 1.86 degrees per molar. Now, delta Tf is equal to I into Kf into molality, where I is the van 't Hoff factor, Kf is molar depression constant, and delta Tf is depression in freezing point. I is equal to 1 because urea does not dissociate. Kf is given as 1.86. Now, mass of liquid water will be equal to 500 minus 128, because 128 grams of ice has been separated. So, 500 minus 128 is equal to 372. Putting all these values in the equation, we will get X equal to 0.5 into 60 into 372 upon 1.86 into 10 to the power 3 equal to 6 grams. If different solutions are given, then the solution for which the number of particles of solute are greater in the solution will have the greater colligative property. This we can understand with the help of an example. Among equimolar aqueous solution of C6H5NH2Cl, CaNO3 whole twice, LaNO3 whole twice, glucose, which will have the highest freezing point. Glucose does not ionize, so the number of particles furnished by glucose in solution will be least compared to other options. Hence, the depression in freezing point is minimum. We can say that the glucose solution will have the highest freezing point. All the colligative properties for the glucose solution will be minimum. There is another example. The molar depression of the freezing point in 1000 grams of water is 1.86 Kelvin kg per mole. Calculate what would be the depression of freezing point of water when 120 grams of urea, 117 grams of sodium chloride, 488.7 grams of barium chloride 2H2O have been dissolved in 1000 grams of water. It is assumed that sodium chloride and barium chloride are fully ionized, that is, their degree of dissociation is 1. First, we are going to take the case of urea. As the urea is non-electrolyte, the number of particles does not change in the solution. Therefore, delta Tf will be equal to 1000 into Kf into Wa upon Wb into Ma. Putting all the values, we will get delta Tf equal to 3.72 degrees Celsius. In case of sodium chloride, as alpha is equal to 1, so number of particles furnished by one particle will be equal to 2. Hence, delta T of sodium chloride will be equal to 2 into delta T for urea, which is equal to 2 into 3.72, which is equal to 6.44 degrees Celsius. Now we are going to take the case of barium chloride 2H2O. Barium chloride 2H2O will furnish 3 ions. Hence, delta T for barium chloride will be equal to 3 into delta T for urea, which is equal to 3 into 3.72, which is equal to 11.16 degrees Celsius. Sometimes some solutes can have normal molecular mass in one solvent and abnormal molecular mass in another solvent. Let us consider one example to understand this. 1.22 grams of benzoic acid is dissolved in 100 grams each of acetone and benzene separately. Boiling point of mixture with acetone increases by 0.17 degrees Celsius and boiling point of mixture with benzene increases by 0.13 degrees Celsius. Kb for acetone and benzene are 1.7 and 2.6 Kelvin kg per mole respectively. Find the molecular weight of benzoic acid in acetone and benzene. For acetone, molecular mass of benzoic acid will be equal to 1000 into 1.7 into 1.22 upon 0.17 into 100, which is equal to 122. For benzene, molecular mass of benzoic acid will be equal to 1000 into 2.6 into 1.22 upon 0.13 into 100, which is equal to 244. So, molecular mass of benzoic acid is 122 and thus it is evident that benzoic acid remains as normal molecular species in acetone but shows 100% dimerization in benzene. That is, in benzene, benzoic acid exists as double the molecule, that is dimer. Here is the structure for dimer of benzoic acid. Two molecules of benzoic acid are bonded with each other by 2 hydrogen bonds. In this unit, we discussed abnormal colligative properties by association and dissociation, abnormal molecular masses again by association and dissociation, want of factor and calculation of want of factor. With this, we also come to the end of the unit solutions, dilute solutions and colligative properties. I hope you are now able to understand this unit in the better way.